All right, so the idea is that you have a function z is equal f of xy, and then you have like a curve, a two-dimensional curve, x of t, y of t. And what they're saying there is that if you do the composition of the function and the curve, then you would actually get a function that is eventually going to be just a function of one variable. What does that mean? That means the resulting function only has a t in it. So there's an x and a y in the original function, but the x and the y are functions of t, so eventually your function is going to be a function of just t. Okay? So does that make sense? So we can say that f of x of t, y of t can really just be represented as a function of only one variable. So this idea of a chain rule, this derivative, has partial derivatives and has regular derivatives. And you kind of have to be able to look at it and identify which one's the partial derivatives and which one's the regular derivatives. Okay? So why don't you guys just soak this in for a minute and try to do a problem, and then we'll see if we can relate this to an actual graph drawing or whatever. So notice the straight D versus the curvy D. Right, so the function z is actually going just to be a function of one variable. And then according to the formula, we're going to take the partial derivative of z with respect to x. The derivative of cosine is negative sine. The sine x plus 4y times the derivative of the inside. Don't forget the chain rule. But the derivative of x plus 4y with respect to x is just 1. So that's the partial of f with respect to x. And now we need the derivative of x with respect to t. So the derivative of x with respect to t is going to be, what? 20? Okay. And then you take the derivative of f with respect to y. So again, the derivative of cosine is negative sine. But this time when you take the derivative of the inside, you're taking it with respect to y. So the x is gone, and then derivative of 4y with respect to y is just going to be 4. So there's an extra 4 that pops out of there. And then times the derivative of the inside, or the derivative of y with respect to t, and that's going to be, what is it, ln? Or that's the integral. Negative 1 over t squared. Right? T to the negative 1, bring the 1 down, you get t to the negative 2 with a negative, so that's 1 over t squared. And you're done. Are you, though? Well, sometimes they would be happy with an answer like this. Other times they would be interested in having you putting it all in terms of t, because the original function after the composition is really just becoming a function of t. So we might be interested in putting the t back in. So all that really means is that you're going to put 5t to the 4th in for x and 1 over t in for y. Why is there all these letters keep popping up? So I think that would be it. Now everything's in terms of t, and then it's all done. Yeah. It depends on what they're asking for. Sometimes they ask you to put in values. Sometimes they ask you to put it in the last set of variables. And sometimes we just ask for that, and so it depends on what they're asking for. Okay. So just to be clear about what these values are, we have the partial of f with respect to x, and this is dx dt, and partial of f with respect to y, and then dy dt. Okay, so those are those little components. Any questions? What does this mean? Can you think of a possible scenario where this might happen? Or let's look at it geometrically. What does this mean geometrically? So you have a two-dimensional curve, and you have a surface that's a function of two variables with a third variable z that gives you, oh, maybe the height or something. So what do you think this could represent? Oh, well, we're doing a geometric point of view, so why don't we see if we can graph it? So we have a cosine of x plus 4y. Okay. I have a feeling that this is probably going to be tough to visualize. Now, space curve is a curve with 3 dimensions. What can I do to try to draw a curve in 2 dimensions? What? Parameterize the curve. Well, we do have a curve, right? It was a 5t to the 4th, 1 over t. What do you think? How would you represent a two-dimensional curve in 3 dimensions? What? Set z equal to 0. I think if you just set z equal to 0, then that might be all good. What's that? Maybe we can, well, it's still hard to see. Okay, so what do you think is happening? Or what do you think we can do? What does the composition of the two functions mean? What does it mean when you put the x and y value? Let's say I pick this one particular x and y value over here somewhere. What does that mean when I put the x and y value from that point into the function? Any ideas? Any ideas? Anyone? Anyone? Well, I think what that means is that you're putting the x and the y value into the function. What do you get? What do you get when I like put 0, 0 into the function? What do you mechanically? What do you do? Do you understand my question? No. So what's happening is when you literally put the x value and the y value into the function, you're putting it into the function, and in the case of a graph like this, you're finding the height of that point above on the function. Okay, one can think about it as projecting it onto the function. So if this is your function, cosine of x plus 4y, right? And then I take my x values from the space curve or from the two-dimensional curve, and I put the x value in for the x value, and then I put the y value in for the y value, then I should be able to see a curve that has the same x and y value as a curve that's on the xy plane, except now the height's going to change. I don't know about that one. It's going from let's go from -3 to 3 like the other graph. And 200 steps. Maybe let's go from -1 to 1. That looks confusing. Yeah, I figured this wasn't going to be a good example. So what's happening here is maybe we'll take the function and go out further. Maybe that'll help. Is that better? All right, why don't we visualize another example? I was thinking of a nicer example where because already the cosine function goes positive and negative. What if we just put everything positive? So we could take that and lift it up. So let's redo another example. So let's visualize this. F x y composed with x of t, y of t. So let's use the same. We can use the same function. That would be z is equal to cosine x plus 4y. And then this time, let's lift it up a little bit. Let's lift it up by 2 units so that it's above the xy plane. So the shifting transformation is the same for the adding something to the outside of the function, just shifts it up. And then let's change the function so we don't have that 1 over t discontinuity. And a really nice set of functions for viewing this as an example would be just a circle. So y is equal to cosine t, or x is equal to cosine t, y is equal to sine t. All right, so let's go back to our graph, our picture, and let's change a few things here. So I'm going to add 2 to this one, and we don't have to go all the way up to 5. I think we can just go to 2 to 2. So there it is. It's been lifted up a little bit. And let's change these functions. So the first function is going to be cosine t. The second is going to be sine t. And then 0. So that we just have a nice circle. Easier to look at? So that's easier to look at. And I think it's going to be easier to view now. So if we take our function, our x and y, change that. And remember that this is the function cosine of x plus 4y inside of the parentheses. And in for x, I'll put in the I'll do the composition where we put cosine t and sine t. Did I put too many parentheses? No, it's okay. Also, what are my limits for this? I went from -3 to 3. We'll go from 0 to 2 pi. All right, so how do you think this is going to look like? Oh, plus 2. So 0 to 2 pi. So that is going to look like, from the top, it's the circle, right? Your x and y are the same. But then your z superimposing the circle. Yeah, so you're putting that circle that's on the xy plane, and then you're just projecting it up onto the surface. So this is how it would look like if we take the surface away. Then this is how the curve would look like. Right? So let's put the surface back, and let's actually do a trace of this function. Let's take the velocity and acceleration vectors out of it. But if you look at the trace, or how this function is being traced, it's just going to go around in a circle. Well, if we look at it from the top, it looks like it's just going to go around in a circle, right? But as you go around in the circle, your height, according to that function in x and y, will be changing. So as you go around, it'll follow the contour, not the contour, but it'll follow the shape of the surface. Okay? So that's one application of something like this where you can try to visualize it. And so that's like a geometrical interpretation for the composition of these functions. There are a few other ways to view this, or a few other applications that we can talk about, and maybe we'll talk about that a little bit later. All right. I don't know if this is a good picture. I need a good viewpoint. So how would we explain this in words? So the composition of the functions results in a projection of the 2D curve x of t comma y of t onto the surface. Okay? So your first curve down here is a curve x of t comma y of t. And this is your surface. Z is equal to f of xy. And the curve up here is not just f of x of t, y of t. The curve has to be described as a three-dimensional curve. It has an x value of x of t and a y value of y of t. And now it's the z value that comes in. So I'm going to put z of t to say that this is really a function of just one variable t, but this is where the projection comes in. So z of t is equal to the function evaluated at x of t, y of t. So this is where the composition happens. That's the composition of those two functions. And that composition really only gives the z component of this projection. Okay? So this is one application. Some of the applications that they talk about gives you a temperature instead of a height, like we're doing. So they say you have a plate, and then the temperature in the plate is T of XY, and then as you move around the plate, your temperature will be changing. So if you move in a specific direction, what's that derivative going to be? What's your change in temperature? So that's another application that you might see. All right. So any questions? So that's your general application. We haven't really talked about plugging in values either, but there are times where we might be interested in plugging in the values, and so I'll let you think about that. Now let's go on and continue talking about other forms of the chain rule. This is just one special case. Okay. So maybe your function f has 3 variables, and then you have x as a function of t, y is a function of t, and z is a function of t. So maybe you might want to compose 3 of them. Well, it kind of just makes sense that you just tack on another one. So the formula that we come up with would be, again, this would be a function of just t. So we're looking at the derivative of f with respect to t. And the d's, again, are straight derivative d's. And so it's the derivative of f with respect to x times the derivative of x with respect to t. So that is one part of it. Then you have the y. And then you have the z. Oops. Don't get your d's mixed up here. I'm starting to. Yeah, well, it's similar to a cursive Q. I was trying to write cursive the other day. I had to look at my phone. How do some of those letters look like? I didn't have to write. I was just writing cursive. By the way, in Calc 1, when you're learning the chain rule, you see that dy dx is equal to dy d something d dt times dt dx, something like that. And then, you know, Calc 1 students always want to cancel. Oh, the dt's just cancel, and then that's all you have left, right? That's the canceling business is not how things work here. As you can see, if you try to cancel things out, I mean, the partials and the regular d's look different, but the whole canceling out business doesn't work here. In fact, you can just use those subscript notations. And then you can even use the prime notation if you want. Shorthand it. But I think it's fun to write all those different D's and not get yourself mixed up. So anyways, in thinking about this, and this is a formula, it looks like there's a lot of special cases, but what we could do is we can generate a way to figure out the different formulas for the different combinations and compositions of functions. So they developed a way to do that. And the way they do that is to use a tree, right? Not a tree growing outside, but That's what it's called, right? A tree? Computer science. This is a tree, right? Is that what it's called? A tree? What is it called? Of course I am. So the book uses uh, a tree notation to try to help us figure out the formulas for these things. Actually, I'm short a variable here. So let me redo my tree. Just adding another one. I actually prefer that since the bottom set of variables is just one variable, I'd actually prefer to just do it this way. Because it all goes down to one variable, if that's okay. The only thing is that we need to label the branches, the connections. And so that might get confusing if we only have one thing down in the bottom. So let's try it anyways. One thing down in the bottom. So we have the partial of f with respect to x as the branch connecting. And then if we go from x to t, we notice that t is the only variable. So we know that this is a straight d derivative, dx dt. And then we complete the other branches or the other connections, df or partial of f with respect to y. And then this is dy dt. And then the partial of f with respect to z. And then dz dt. And then what you do to help you form your formula for the derivative is if you want to take the derivative of f with respect to t, df dt, what you would do is you would go from f to t and find out all the different paths to get there. So one way to get there is df dx and then dx dt. And then you get there via df dy, dy dt. And then you get there by going df dz, dz dt. And then that's your formula. Okay? Yeah. Well, geometrically, it'll be harder to explain because this is 3 dimensions and the output would be a 4th dimension. So that idea geometrically would be more difficult to visualize. But if we imagine F as a temperature and XYZ is a space, right? Let's make up a problem. So suppose T of XYZ gives a temperature in a room for any point in space, right? So let's say, suppose I have a formula for the temperature in this room. Let's say there's a heat source somewhere, maybe at the origin or something like that. So then I can describe the temperature at any point in this room. And then let's say a bee, a fly, is flying around on the path x of t, y of t, z of t. So there's a bee flying around. Okay. So at t equals t naught, so at some value, that this bee is flying, we can find the rate of change of temperature that the bee is going to the fly is going to feel as the fly moves from that point and keeps going in the path that it's going. So what would that be? The rate of temperature then is dz dt, or dt dt, d capital T, d little t. And then we need to evaluate this at the given value t naught. So that's how we can imagine something like this happening. I think I just made up an exam problem right here. Okay. All right. So I don't have an actual problem made up yet. It'll come on the exam. But imagine making up a problem with a function with an x, y, and a z in it. So a function of 3 variables. And then imagine making up a path x, y, z, x of t, y of t, z of t. And then just give yourself a t value, t naught equals 1 or t naught equals 0. And see if you can come up with a problem. Actually, see if you can come up with a problem, give it to me on Monday, and then maybe I'll use that same problem for the test. Maybe. All right? But that would be a way to visualize something like this. There might be a way, but we need one more piece of information that's a couple of sections from now. Gradient. Have you guys heard of the gradient? Maybe it's in the next section. So we'll talk about that on Monday. So see if you can hold your question and see if it will get answered next time. I don't know if it will or not, but we can hope. All right. So these types of problems end up being just a function of one variable, but we can go more than that if we want. So more cases of the chain rule. Sounds like a disease. More cases of the chain rule. More cases of the disease. So maybe your x, y, and z, or x and y, are not functions of just one variable t. Maybe your x and y happen to be functions of 2 variables, s and t. Well, they gave the formula for this, but before we write down the formula, before we think about what that formula is or where it comes from, let's actually derive that formula using the tree notation. I was going to say the tree way of doing it. So f, you can say, is a function of x and y. And then now x is a function of s and t, and y is also a function of s and t. So in the book, again, they write s and t twice, but I'm going to write s and t once and say x is a function of s and t, and also y is a function of s and t. This is where it kind of gets confusing. But I encourage you to look at the book to see their thing, their notation, see which one works easier for you. Because like I said, you still have to label it, and the labeling is going to get kind of messed up. Or not messed up, but it's going to get a little messy. But if you keep your, I was going to say, keep your cool, it won't be too bad. Don't panic. So the partials with respect to x and y are going to be partials with respect to x and y. But when we go down to the next level, before we only had one variable, so we had a straight d derivative. But now x is a function of two variables, s and t, so we have to also write the partial derivatives for those. And so is y. So when we write these things down, we're using the partial derivative notation. Partial x with respect to s, partial x with respect to y. And then here we have the partial y with, oops, this is t, sorry. Partial y with respect to s, and partial y with respect to t. So notice that I have two variables in the end. Everything's going to be a partial derivative. So really, I don't know why I didn't copy this other one, but there's two formulas that we need to consider. The derivative of f with respect to s, and the derivative of f with respect to t. So we have two sets of partial derivatives to look at. And then the way we would trace it down the tree is that if we say we wanted the partial of f with respect to s, what we're going to do is we're going to try to find all the ways to get from f to s and then add them all up. So through x, we would have the partial of f with respect to x and the partial of x with respect to s. And then through y, we would have the partial of f with respect to y times the partial of y with respect to s. And those are the only paths to get down to the s. The other paths go to the t, so we don't need to worry about that. Okay? So this one, I haven't really attempted to think about how to visualize this. So if you want to think about it, be my guest. Otherwise, let's just do an example. So let's find the partial of z with respect to t. Okay, so take a few minutes to think about that and give it a shot in your notes and see if you can, if we come up with the same thing. I think I got something. Hope you guys got something similar. So the derivative of the arctan is 1 over 1 plus something squared. And the chain rule tells you that you have to take the derivative of what's inside of the arctan after that. So the inside of the arctan is x squared plus y squared. If you take the derivative with respect to x, the chain rule, the calc 1 chain rule, tells us that we have to multiply by the derivative of x squared plus y squared with respect to x. So that's 2x. So this is the partial of f, or partial of z, with respect to x. And then now we want the partial of x with respect to t. And so s is a constant. The derivative of ln is 1 over? Okay. The derivative of ln is 1 over t. The derivative of ln t is 1 over t. So s times 1 over t. And then the next one is the partial of z with respect to y. And then I left out my 2y over here. So the derivative is the derivative of arctan is 1 over 1 plus something squared times the derivative of something with respect to, in this case, with respect to y. And then the last part, the last bit, is just the derivative of y with respect to t. And so t, and then s, e to the s is a constant, so it's just e to the s. Okay? So you can also plug in the values in for x and for y. By the values, I mean the functions. So x is equal to s ln t, y is equal to t e to the s, and then you can put that into these functions and then try to simplify it if you want, or you can leave it like this. But again, it depends on what they're asking for. Sometimes we're interested in evaluating this at some point. So why don't we take this same function and evaluate it at some point? And so at some point means we're going to evaluate it when s and t equal to something. So let's say you can convert everything, or you can take advantage of what those functions are equal to before you convert it, if that makes sense. Let me see if I can rewrite this. So we want just to get used to some notation, find dz dt evaluated at, let me see if I can, which one's first in the alphabet, S or T? S is first, right? So let's say S is equal to 0, just to make it nice, and Y or T is equal to 1. So dz dt, the partial of z with respect to t, evaluated at 0, 1. And just to be clear about that, we're saying that s is equal to 0 and t is equal to 1. Okay? So we have all the information already. We have the partial derivative already worked out for us, right? So all we have to do is put 0 in for s and 1 in for t. So if we do that, then things are going to happen. But there's x's here and y's. How do you think we can deal with x's and y's? There's x's and y's right here, right? So to help us out, what we could do is we can figure out what x evaluated at 0, 1 is, and what y evaluated at 0, 1 is equal to. So s is equal to 0 times ln of 1, that's just 0. And for the y, it's going to be 1 times e to the 0. And so that is equal to 1. So it looks like x is equal to 1 and x is equal to 0 and y is equal to 1. So we would put that into the function. Into your derivative. So we can say that dz dx evaluated when x is equal to 0 and y is equal to 1. So this is the case where you don't have to put everything in terms of s and t anymore, because then you're figuring it out along the way. So this is, I'm going to put the 2x in the numerator, and then I'm going to put the 1 plus x squared plus y squared squared in the denominator. So that's the derivative, right? Just rewrote it. I'll put 0 in for x, and I guess it doesn't matter what this is, because that's just going to be 0 anyways. And then I'll put 0 in for x and 1 in for y for the partial with respect to y. So I think that's a 2y up on top. 1 plus x squared plus y squared. Oh, annoying. So this time I get 2 times 1 in the numerator, 1 plus, and I think this is just going to be 1. So this whole thing is going to be 2 over 2, which is 1. What? I guess we need to do that too. So let's do that real quick. Do it off to the side here since we didn't leave ourselves much. I didn't leave myself much room. Dx dt evaluated. This time I'm putting in 0, 1 for s and t. And that comes from this derivative right here, right? So 0 over 1. And then the partial of y with respect to t, where s is equal to 0 and t is equal to 1, is going to be, that's e to the s, which is just 1. Okay, so putting it all together, partial of z with respect to t, evaluated at 0, s is equal to 0 and t is equal to 1, is equal to the dz dx evaluated at that point, the dx dt evaluated at that point, the dz dy evaluated at that point, and then the dy dt evaluated at that point. So that's just equal to 1. Okay? All right, there's a cool numerical problem somewhere in the book. I don't know if you guys have a homework assignment that's like that, but it'd be good to take a look at. That's a chain rule. Okay, a lot to think about. See you guys next time.